Yeah, so I'll talk about measuring the electron's electric dipole moment with ultracold YBF molecules. Dave has explained everything beautifully already, but we'll just reiterate the principles of how you measure an EDM. So here is a cartoon of a particle. It has a spin, which is the blue arrow, and associated with the spin is a magnetic dipole moment. So if I take this particle and I put it in a magnetic field, there will be an interaction between the magnetic dipole moment and the applied magnetic field, which exerts a torque, which causes the spin to precess. My particle here also has an electric dipole moment, as you can tell from its egg-shaped charge distribution. So if in addition to the magnetic field, I also apply an electric field, let's say parallel to the magnetic field, there will be an additional interaction. It's the interaction between the electric dipole moment and the applied electric field. And that will exert an additional torque, which will cause the spin precession frequency to change. I suppose it speeds up a little bit. And then if I put the electric field in the opposite direction, anti-parallel to the magnetic field, then the torque will be in the opposite direction, and the spin precession frequency will slow down. So actually all you have to do to measure the EDM is to measure the change in the precession rate when the electric field direction is reversed. And if we're talking about electrons, then it turns out that the sensitivity of such an approach is enhanced enormously when the electrons are bound up inside heavy polar molecules. The extremely naive picture looks something like this. Here's a heavy polar molecule. Apply an electric field in the lab, and the molecule polarizes along the electric field direction, and now the electrons are seeing the internal electric field of this polar molecule, which can be enormous. In the case of the YBF molecule that I'll speak about, we apply an electric field in the lab of about 20 kilovolt per centimeter, and this effective electric field is about 20 gigavolts per centimeter. The statistical uncertainty of a measurement such as this scales inversely as the product of these three quantities. So the effective electric field, which can be enormous for heavy polar molecules. The square root of the number of particles, which can be large, especially if you use neutral molecules. It's quite hard to make it large if you have trapped ions in an ion trap because of the Coulomb repulsion between the trapped ions, but you can make it large for neutral molecules. And then the spin precession time, which can be large, provided the molecules are at low enough temperature, and particularly if they're trapped. So our approach, of course, is to try to make all three quantities large by using neutral, ultracold, or trapped heavy polar molecules. So I'm going to talk about two experiments, both using ultracold YBF molecules. The first experiment uses a beam of these molecules. That experiment is built, it's working. And the second experiment aims to use molecules in an optical lattice, which we are still developing. This is what the beam experiment looks like. We produce a beam of these ytterbium fluoride molecules by cryogenic buffer gas cooling. It's a pulsed beam moving at about 160 meters per second. And it comes out of this cryogenic buffer gas source. It's diverging. But then it passes through this two-dimensional optical molasses, which reduces the spread in transverse velocity to small values, so that now you have a very highly collimated molecular beam that can travel a long way without any significant divergence. We prepare the molecules in the absolute ground state using some optical pumping techniques, and then these molecules pass into this magnetically shielded region where the spin precession happens. Okay, so we first of all prepare the spin, polarize the spin along the y direction using stimulated Raman adiabatic passage, stirap. The spin then precesses around in a small applied magnetic field and a large applied electric field, and then we use a second stirap to analyze the spin direction. If the spin is along y, then this second stirap transfers the molecules to one hyperfine state, and if it is turned around to be along x, then the molecules are transferred to a different hyperfine state. And then in the end, we just measure the populations in those two hyperfine states by laser-induced fluorescence detection onto photomultiplier tubes and onto CCD cameras. So we've done a lot of work understanding all parts of this experiment. I will just show you some pictures Here's some pictures from this end camera, this end CCD camera here, which looks down the beamline. So you see the density of the molecular beam at the end of the beamline here. This top picture is with the laser cooling off, and maybe if you just about squint, you can see a tiny little bit of signal. And this bottom picture is when we turn the laser cooling on. You see this very bright signal on the CCD camera. So this is just illustrating the importance of the laser cooling step here. We have in this experiment about 1 million ultracold molecules per shot, and the temperature of this molecular beam is below 100 microkelvin. Here are some pictures from these side-on photomultiplier tubes that we actually use to read out the signal in the experiment. And this is the particular case where we've prepared the spin along Y and allowed it to precess by 90 degrees. In that case, all of the signal should appear on the second camera and none on the first camera, and you see we approximate that situation. Actually, the cameras, it turns out, have been really very wonderful detectors. They have very high quantum efficiency. They give us this very useful spatial resolution, and it also turns out that they have useful time resolution. So actually, this is the time of flight of the pulse molecular beam as it passes through the detectors here, recorded on the CCD and on the PMTs. And you see that we can actually, a little bit, resolve the time profile of the molecules as they pass through, which gives us velocity resolution in the experiment, which turns out to be very helpful. The PMTs, of course, have much higher time resolution than the CCDs, but we've chosen here just to bin it in the same way. So this experiment is working. Here's some results from the experiment showing what we call the asymmetry. It's basically the difference in the signal between the two detectors as a function of the applied magnetic field here. If the experiment was working perfectly, this would just be a cosine function. So it's not quite perfect. There's not perfect contrast in the experiment, and there's also an offset on the signal. Both of those things are due to imperfect stirrup in the experiment. And if you want to understand more about why the stirrup isn't perfect in our case, then please come and talk to me about that. From this data, we can infer the shot noise limited sensitivity of this experiment, which is sitting at 7.5 times 10 to the minus 30 e-centimeter in 24 hours. So that's a useful level of sensitivity. Now, I should emphasize that this is the shot noise limited sensitivity, and there are many other sources of noise in the experiment which we're currently trying to bring under control. So our current aim is to demonstrate this level of sensitivity by Christmas, this Christmas. As Dave mentioned already, it's actually very important in these experiments to control noise, control magnetic noise and magnetic-related systematics, and we've done a lot of work to do that. Let me give you some of the requirements here. So to reach our target sensitivity, we need to apply an electric field of 20 kilovolt per centimeter with leakage currents below 100 picoamps. The magnetic noise needs to be below 100 femtotesla per root hertz at 1 hertz. The background magnetic field should be below a picotesla with gradients below 10 picotesla per centimeter. There should be no ferromagnetic materials anywhere and no metals inside this spin precession region because the fluctuating charges inside the metals produce too much magnetic Johnson noise. And the magnetic field that correlates with us reversing the electric field has to be below 0.1 femtotesla. So these are all very challenging requirements, and we've come up with some we think, nice solutions, which may be actually useful for some of your own experiments. So I'll just say a little bit about these. So we use, instead of metal electric field plates, we use ceramic electric field plates. They're built from alumina with a thin layer of titanium nitride. The titanium nitride is a conductor, but it's very thin, and so it doesn't contribute any significant Johnson noise. And these electric field plates are then mounted up inside a glass vacuum chamber, which then sits inside this 4-layer magnetic shield. You can read all about this work in this long paper here, and I'll just give you the highlights, so the key results. So we measure a shielding factor, which is 10 to the 5 in one direction, 2 times 10 to the 6 in the other. The Johnson noise we estimate to be 13 femtotesla per root hertz. The total magnetic noise we measure is 50 femtotesla per root hertz at 1 hertz. Our magnetometry can measure to this 0.1 femtotesla precision in about 100 hours of data taking. And we currently have leakage current sitting at 600 picoamps at 20 kilowatt per centimeter, which is a bit too high. We're still working on that. All right, so that's where we are on the beam experiment. And then moving on to the experiment with molecules in a lattice. So the plan is to take this molecular beam, decelerate it to rest using radiation pressure, and then capture the molecules in a magneto-optical trap. There they can be cooled down to 10 microkelvin and then transferred into an optical lattice where the eEDM experiment will be done. In the optical lattice, the spin precession times of many seconds are feasible. This radiation pressure slowing step turns out to be particularly difficult, and so it was important to us to start from a very slow molecular beam. And to that end, we developed a new cryogenic buffer gas source. It uses this two-stage buffer gas cell, which we cool to 1.8 Kelvin instead of the usual 4 Kelvin. And again, you can read all the details of that in this paper here. But the bottom line is that we're now routinely able to produce molecular beams with a peak speed of about 75 meters per second. That's a lot slower than a standard cryogenic buffer gas source, but still nowhere near slow enough to capture the molecules in the MOT. To be able to capture them, to be able to slow them to the required velocity and then capture them in the MOT, every molecule has to scatter about 10 to the 5 photons, which turns out to be quite difficult in ytterbium fluoride. So here is the main laser cooling transition that we drive in the molecule. And our excited state here can decay to several different vibrational states down in the ground electronic state, but with ever diminishing branching ratio. Okay, so this is a kind of closed problem. This is a solvable problem. We simply repump all of these vibrational states using more lasers, and that bit is fine. And it turns out that in ytterbium fluoride, there are also some metastable states, some low-lying metastable states that arise from inner shell excitation of the 4f electrons on the ytterbium ion. We call them the 4f whole states. For those of you who are familiar with ytterbium, this is the equivalent of the clock states in the ytterbium plus ion. Our excited state here can decay to these 4f whole states with branching ratios that we cannot neglect. When we first started this project, we really didn't know anything at all about these 4f whole states, and now we've done a lot of work to understand them, both theoretical and now also a lot of laser spectroscopy, and you can read about that in these two papers here. Having learned a lot about them, we then tried to drive the population back again to close off this leak. We actually failed to do that, or at the moment that is not working. And we think that the reason that's not working is that these 4f whole states actually decay to the ground state much more rapidly than we had originally estimated. So the population, having reached here, decays actually back to the ground state, which gives us a new problem. The population rains down to all of these other states here, which we now have to repump. So we do that using microwaves to couple together the rotational states down here and some more lasers to drive these other transitions. And then when we do all of that, everything starts to work. Okay, so here I show some slowing data. This is the velocity distribution that we measure. First of all, in gray with the slowing laser turned off, and here in red with the slowing laser turned on. And here the microwaves are turned off. Okay, so we haven't closed this leak. And what you see is that most of the population is just disappearing. And then we turn the microwaves on, and we recover the majority of that population. And you see clearly that we're able to slow down the molecular beam and create a substantial fraction down here at low velocity. Just say show a few more graphs on this radiation pressure slowing. So here's the slowing that we see as we increase the amount of time we apply the slowing light on. And maybe you can just about see that the longer we turn the slowing light on, the slower the molecules become. Here is the change in the peak velocity after slowing as a function of the duration, and we see this linear dependence. And then most importantly, we're creating molecules at low velocity. Okay, so this graph is showing the the fraction of the molecules that we measure below some upper threshold velocity as a function of the slowing duration, and in all cases, we're creating more molecules at low velocity. Some of these molecules are now slow enough to be captured in a MOT, and we've, over the last month, really been focusing hard on trying to get the molecules in the MOT. And I think I would say that we have the first indications that we have some magneto-optical confinement. At least we see that the molecules are hanging around longer when the MOT has one circular handedness versus the other, and that the handedness you need reverses when you reverse the magnetic field gradient. So we have the first signs that it's working, but we're not quite confident enough yet to say that we have a MOT. Hopefully we will have that very soon, and then we can move on to the rest of the experiment. And I'll just show you the designs that we have now for the lattice experiment. So here is the magneto-optical trap where the molecules will be trapped. We will then use subdoppler cooling to bring the temperature down to about 10 microkelvin. That step we already know how to do. And then we will transfer the molecules to a one-dimensional optical lattice along this axis here. This will be a movable 1D optical lattice, which we will use to move the molecules from this MOT region into this magnetically shielded region. And if we just open up the magnetic shields here, here's the 4 layers of magnetic shield. This is the lattice axis here, and you see this long glass tube which is terminated in a glass cell. Inside the glass cell, we will put these electrodes, which are the similar design to the ones I showed you before. They're ceramic electrodes. Okay, so the spin precession measurement will then be done with molecules sitting in between the electrodes here. I'll just very briefly say something about comagnetometry, because one of the most difficult problems that we have is dealing with systematic errors relating to magnetic fields. And the molecules themselves can act as comagnetometers. So the state that we use, the rotational state that we use for the eEDM experiment is this red one here. It's the ground rotational state. It's sensitive to the eEDM, and it's also sensitive to magnetic fields. But there are other rotational states in the molecule. For example, this blue state, which at 18 kilovolt per centimeter has no sensitivity to the eEDM, but is still fully sensitive to the magnetic fields. So this way we should be able to isolate the eEDM of interest from any magnetic effects. So that brings me to the end. Let me thank the team of people who've been working on these 2 experiments, highlight that Ben, Reese, Guanchen, and Jongsuk are all here, and that we have posters, so please come and talk to us. I reiterate my thanks to the foundations for funding this work, and thanks for listening.